Hey guys, today we're doing exponential growth and decay, but we're going to do exponential regression. So we've already done linear regression, just a quick reminder. So if I give you all of this data, and it makes a line, obviously, I'm going to put this into Desmos, this table in Desmos first. We did this at the very beginning of the year. I'm going to do plus table. I'm going to put in all those values, so 10, 13, 15, 19, and 21. And then my y's were 65, 72, 75, 85, and 90. Then we came down here. This is where we did the y1 squiggly. That's what the formal name for it is called. It's called exponential regression. I mean, not exponential, linear regression. We're doing exponential regression today. So it gives you your M and it gives you your B. So if I were to find the regression for this, let's move this over for a second. We use this data, we plugged it in, to a table on Desmos, and then we plugged in y1 squiggle mx1 plus b. And then when we got out, we got our m and we got our b, right? So our m and our b, M was 2.26 and B was about 42.18. So then if I were to plug it into slope-intercept form, it would be y equals 2.26x plus 42.18. So what Desmos is doing is it's making something called a line of best fit that goes through most of these points on my graph. So if we were to look at my graph, notice there's all my points, and then my line went through the best fit. It went through those points. So without this, it didn't make the line. It just has the points, and then when I put that back in there, it makes the line go through it. So I'm finding the line of best fit. Or we also called it trend line, either way. Trend line or line of best fit. So guess what? We can do the same things with exponential functions. Same thing we do with linear, we can do with exponential. And we call this, if linear functions are called linear regression, these are called exponential regression. Okay, so we're going to do the same thing. You've got to first put the table of values in. All of this stuff we're not going to do. We are going to use Desmos instead. Desmos. So I'm going to first plug all this in just like I had the linear. All I'm doing is making the table. So I go to plus table. I'm going to put it in. 0, 1, 2, 3, 4, 5, 6, 7. We don't need 7. Okay. At 0, we're at 110. 1, we're at 147. 2, we're at 172. 3 is 233. 4 is 318. 5 is 395, and 6 is 433. So this time, instead of doing my linear regression and remember, linear regression is just standard form. So standard form is y equals mx plus b. The only thing we're changing is making the equal a squiggle and putting y1 and x1. So same thing here. Remember, exponential standard form is y equals a times b to the x power. Regression is y1 squiggle a times b to the x1 power. That's what we're going to be using. That's regression. So when we go here, y1 squiggle a times b, you can just put them right next to each other, to the x1 power. When that happens, it gives us our a and our b. Now, I don't know what's going on with Desmos. I will look into it. And that is not technically our a, because remember, a is our starting point. It's where it crosses the y-axis. Well, we have the point where it's crossing that y-axis, right? It's crossing way down here at 0, it's 110. So I don't know why it's saying 120. I'll look into that. But my A is not that. But we know the initial amount is, A is 110 because that's when we're at 0. But it will give us our B. So our B is going to be this, the 1.24-ish. Okay, so if I have A and B, it's y equals A, so 110 times the 1.24 to the x power. Again, you can always write this like y equals 110 and then 1 plus 0.24 to the x power, because it's either 1 plus or 1 minus. And because we have the 1 plus, that means that this is going to be a growth, exponential growth. So it's how many internet hosts were there in 2001? Well, this says years since 2001. So if it's been 0 years, we're still in 2001. So we're at 110. That's our starting point, initial value, our y-intercept. So 110 million. How many internet hosts are in 2005? So again, if we're 0 years, that's 2001. 1 year is going to be 2002. 2 years after 2001 is 2003. 3 years is 2004. 4 is 2005. 5 is 2006, and then 6 is 2007. So I'm looking for year 2005, which is 4 years after 2001, which is 318 million. And it says, what is the average growth or decay? And again, we already said it was growth, and it's growing by, we can't include the 1, but it's growing by the 0.24. Or I would prefer, if you move that decimal over, it's going to be 24%. Because it's a rate. Rate should always be a percentage. And it says, how many internet hosts in millions are there predicted to be in 2017? Well, I have the function, right? Y equals 110 times 1.24x. All I have to do is replace x with what I want. Now, I'm not going to put 2017. And I'm also not going to put 17, because remember, it's years since 2001. So since I'm starting 2001, I've got to go a year back since we're not starting in 2000. So it's really going to be x equals 16 years past 2001. So everywhere I see an x, I'm plugging in 16. So if I go to Desmos and plug that in, I've got 110 times 1.24 to the 16th power, which is 436.68 million. Which makes sense because we're growing exponentially, so it's going up by quite a bit each time. So it makes sense after 16 years that we've grown that much. Okay, let's look at number next. So this one says the table below shows the population, Y, of Middleton, where X is the number of years since 2000. So again, we're starting in 2000. So 0 years past 2000, I'm still in 2000, right? So this one asks, what's the population in 2000? Well, it's 5,005 peeps. Then in 2005, I'm going to go down all the way to year 5. That's going to be 2005, which is 12,420 peeps. Then we want to model the data. I know what A is. I know my A is the starting point. I'm starting at 5,005. My B I can find by doing my regression. So again, I'm going to make my table. I'm going to put in 0 through 7. And type in all of my Y values. 12. Yeah, 6 is 14,000. 1 is 18,010. So a lot to plug in, but not terrible. And then it's y1 squiggly, ab to the x1 power. Again, we're going to ignore that. We know it's 5,005. I don't know what that's doing. Again, I'm going to look into that and figure out what's happening. But 1.2 is my b. 1.2. Okay. So if I were to write an equation, it'd be y equals 5,005, 1.2 to the x power. And then it's asking, is it growth or decay? Well, it's growth because it's greater than 1, right? And it's growth by 0.20, or if I move that decimal over, 20%. It says, what's the predicted population in 2011? Well, I started in 2000, so 11 years after that. So I'm just going to take my function and instead of x, I'm going to plug in 11 everywhere I see an x. So we're just going to plug that into Desmos. So here we go. Desmos, I've got 5,005, 1.2 to the 11th power, which is about 37,187.57-ish. Now, think about this. We're talking about people, population. I can't have 0.57 of a person. So we need to go ahead and round that up to be approximately 37,188 people. It's a little off there. You can't have that half of people, but rather round up than count somebody out. Okay, last one. So original cost of the car. Well, if it's the original cost, it's 0 years old. So I bought it and it was $25,000. How much was the car worth after 5 years of owning it? So I'm going to go down to where it says 5, and it was now worth $11,203.56. Okay, so A is the initial amount. That's my y-intercept. That's going to be $25,000. And to find my B, I've got to plug all of this into Desmos. I think I've already done. Let's see if I can find it. Nope. Okay. We'll just change these. 7. Okay. So 25,000. 21,462.50. 2 is 17,881.88. 3 is 15,506.66. 4 is 12,919.65. 5 is $11,203.56. 6 is $9,523.03. 7 is $7,934.28. Again, not hard, just tedious. 8 is $6,880.39. 9 is $5,732.52. And 10 is $4,872.64. Okay. Y1 squiggly AB to the X1 power. And that's a little off, not sure why, but our B is about 0.85-ish. Okay. So then if I were to write my equation, it'd be y equals my A, which is 25,000, my starting amount, 0.85 to the x power. So since it's less than 1, it's going to be a decay. less than 1. And to find the rate, I do 1 minus, because it's a decay, 1 minus 0.85 is 0.15, or 15%. And it wants to predict a value when the car is 13 years old. So again, I'm just going to plug in using my function, 0.85, now to the 13th. And when we do that, we get 2,500.85 to the 13th power is about $3,000, $3,022.64. Okay. And it wants to know, what is the value of the car for in what year is the value of the car less than 1,000? So I think the easiest way is to go to Desmos, plug in your function, make it into a table, and then we're just going to go until this is less than 1,000. So notice I'm at 4,000, 1,500. Okay, so year 19, it's 11,039. In year 20, it's going to be less than 1,000. Year 20, it's $968.98. And that's it. Pretty straightforward. Plug into Desmos, and I will look on the Desmos and why it's off on the A and figure that out for y'all. So for now, just look at the tables. It'll tell you exactly what your A is. That's your starting point, initial value. Y'all know how to find that. And then just doing the regression and finding what your B is, and then making your formula. Y'all know how to go from there. Bye, y'all.